Hello, and thank you for joining us today for our Unit 3 slides, Centripetal Forces and Gravity, made by the Irvine High School Physics Club. Let's get started. So as you can see, here we have a problem regarding centripetal acceleration and centripetal forces. We have an object of mass m swung from the end of a string with length L in a vertical circle. If the time of one revolution is 2 seconds, what is the tension in the string at the top and at the bottom? So notice that this is going to be a problem on uniform circular motion. We know that we have a few formulas handy. Most importantly, that the centripetal force, net force, is equal to mass times velocity squared over the radius of its motion. So, if you want to take a chance at the problem, then you can pause the video right here. Else, we're going to move on to the next slide. So the very first thing that we should be aware of, because we're talking about uniform circular motion, is that the object will always move with a constant velocity around the circle. So at the top, at the middle, at the bottom, left and right, every single point is going at that same velocity. So we can essentially say that because even though we're looking at the cases for the top and the bottom separately, because the tension is different, the velocities are still the same. Okay, so at the top, we write our simple force equation. We know that it's undergoing uniform circular motion, meaning we can say that the net force is also equal to the centripetal force, which is equal to the forces towards the center away minus the forces away from the center. And remember, since we're talking about centripetal force, we automatically assign the direction pointing towards the center of the motion, right? The imaginary center in this case, it's always going to be positive. So everything else would not be like the other direction, the centrifugal direction would be negative. So when we say F2 center and F away center, we can also rewrite this as F down minus F up, simply because in our diagram here, the forces to the center from the top is going to point down, right? And away from the center, it's going to point back up. So we have what is going downwards? Well, we know gravity is going downwards, obviously. Gravity always points downwards. And what else do we have? Well, we also have tension, right? Because it's being pulled with a string, and towards the string, the other end of the string would mean going downwards too. So the tension is actually pulling inwards through the string, meaning it's also the same direction as gravity, and therefore we can add them up. These are all F down forces. And at the top, that means that there are no forces going upwards, right? So that's just going to be 0. So f of g plus t of top minus 0, so we can cancel that out effectively, is going to equal mv squared over r. And something important to note is there's no normal force in this case. Why? Well, simply because the object is not on a rail, or it's not like a roller coaster where it's on a rail, right? It's just in that circle, that imaginary circle, that path that it travels in. This circle over here in a diagram is not necessarily showing that there's a rail or something physical that it's sticking on. No, in fact, it's actually being turned around with a string. So given this, we do not worry about any normal forces. So we have gravity and just gravity and tension. Now let's look at the bottom. Same idea, there's no normal force, as the problem did not specify that it was on something physical. So we have applied the same concept, right? The net force is equal to the centripetal force at the bottom. And at the bottom, notice that to center, the forces pointing to the center is now going upwards, and the forces away from the center are going downwards. Kind of opposite of what we had earlier. But in fact, it's not that much harder. You just need to know that tension, right? Tension always points towards the center. So tension is always going to be positive in your centripetal force equation. However, gravity is always downwards no matter what, right? It doesn't matter if you're at the bottom of the circle or the top of the circle, gravity is always going to act downward. Meaning, for the net equation, you have to write T bottom minus Fg because Fg is actually a force down. It's a F subscript down. So we have T bottom minus Fg is equal to mv squared over r, right? So that's our equation for the bottom. And on the next slide, we shall continue investigating this and plugging in a few concrete values. All right, so now we have to kind of take our information from the problem, stuff that the question directly gives us, and apply it here, since we have our basic formulas down. So notice that there's one thing we haven't used yet from the initial problem statement. The fact that the time of one revolution is exactly 2 seconds, meaning that we can effectively write an equation for the velocity that we have so far. Right? Velocity is equal to distance over time. That is a basic formula that we all should know. It's just basic simple kinematics, right? So given that formula, we can plug in what we know for d and t. Well, one revolution is just going to be one times the circumference, right? It's just going to be the circumference of this circle, actually. Well, what is the circle's radius, right? The circle's radius is simply L. As we're given initially, the string has the length L, and the string is always going to be the radius in this scenario. So we're going to have 2 pi L over capital T, because we're given that it takes capital T seconds to travel one revolution. So now we want to take this value and plug it back into our previous equation, right? For at the top and at the bottom, we both have equations for mv squared over r. Now we're going to plug this in for mv squared over r, right? So at the top, that means that mv, or essentially we're also going to make a substitution for our f of t. So mv plus the tension at the top is equal to m times 2 pi L over T squared over L. Right. And make sure, if you don't fully understand, make sure you pause the video so you take a moment to kind of digest everything. And once you have this result, however, it's really easy to solve for the tension at the top, right? And once you're done with that, you just simply move on to the bottom. Same situation here. You're just going to plug in V, plug in mg for f of g, because gravity is always going to be mg, as we all know, and replace all instances of the radius with L, simply, because we're given that fact. And solve for t bottom. So once you have those two values, you should be able to answer the questions. All right, so we just finished our centripetal force problem. Now let's take a look at gravitation. Gravitation, this unit is going to be pretty brief because we're just going to be looking at one formula, and that's just the f of g. F of gravitation between any two objects is going to be the constant g, big G, times the first mass, and times the second mass. All of this over the radius squared. And as you can see, you're given the value of g. You don't have to memorize this, but it's good to keep it handy just in case. And something important to know is that r is not the radius in this case, but it's actually the distance between the centers of these two objects. So if we're looking at a case of two planets, we're not going to be saying the radius is the distance between the two planets' surfaces, right? Because those aren't the center masses of the planets. In fact, we're going to be using r as the distance between the center of masses of the two planets in our case. So make sure to know that, because you're going to get the value of f of v wrong if you treat the surface of the object like the center, when it's clear those two are clearly different things, right? And also you want to know that every object has a gravitational pull to another, right? So you always say any any ordinary object, the ones you see on your desk right now, your pencil, eraser, these all exert a gravitational force on you, and you also exert one back on them by Newton's third law of pairs. But you have to know that this is mostly negligible. Although gravitational force isn't attractive, you're not going to be instantly attracted to every object that you see on the ground, on the table, right? Most of these are really, really negligible simply because, as you can see for our formula here, the value of big G is really, really small, meaning the force is really, really small. And as a result, the acceleration, whatever acceleration that the object is making you go to it with, is also going to be really small. It's a given. So usually only objects, big objects like planets, have the ability to attract you gravitationally, as we can see in the case of Earth, right? Earth is definitely a valid case because we're attracted to it gravitationally. If we jump up, the reason we go back down is because we're in a gravitational field. And that gravitational acceleration is actually having some effect on our motion, right? But it's just in general good to know that gravitation is only really relevant when we're talking about very large objects. All right, so this is about it for our lesson. Thank you again for watching. Make sure to reach out to us on the line at Kids IHS for any questions that we can answer. Uh, and we're pretty active on our social media in general. And so, with that said, our next lesson will probably come out in a week or so. Hope to see you then, and thank you again.